The sun. Our cosmic lifeline. The sun. It's a word we utter daily, a presence so constant in our lives that we often take it for granted. Yet this blazing orb of gas, seemingly fixed in our sky, is far more than just a source of light and warmth. It is the very engine of our solar system, the driving force behind virtually every process on Earth. From the simplest photosynthesis to the most complex weather patterns. Without the sun, our planet would be a frozen, desolate rock, utterly devoid of the vibrant life we cherish. It is, quite literally, our cosmic lifeline. Think for a moment about the sheer, undeniable influence of the sun. Every plant that grows, every breath we take, every drop of rain that falls, all are ultimately powered by solar energy. It warms our oceans, drives atmospheric currents, and fuels the intricate cycles of nature. On a grander scale, the sun's immense gravitational pull holds our entire solar system together, guiding planets, asteroids, and comets in their perpetual dance around its fiery core. But the sun isn't just a local powerhouse. It's also a Rosetta Stone for understanding the universe. As a seemingly average star, studying our sun provides invaluable insights into the lives of billions of other stars scattered across the cosmos. By unraveling the mysteries of our own star, we unlock secrets about stellar formation, evolution, and the very fabric of the universe itself. It's a cosmic laboratory right on our doorstep, offering clues to questions as vast as the origin of elements and the ultimate fate of galaxies. Humanity's fascination with the sun is as old as civilization itself. For millennia, cultures around the globe revered it as a deity, a source of life, and an object of profound awe. Ancient Egyptians worshipped Ra, the sun god, believing he sailed across the sky daily, bringing light and order. In Mesoamerica, the Aztecs built vast pyramids aligned with solar movements, performing rituals to ensure the sun's return. These early interactions, though rooted in mythology, laid the groundwork for systematic observation. The first truly scientific steps came with early astronomers. Ancient Greeks, though often geocentric in their worldview, made remarkable observations. Anaxagoras, as early as the 5th century BC, proposed that the sun was a fiery rock, not a god, a radical idea that led to his exile. Later, Aristarchus of Samos, in the 3rd century B.C., even suggested a heliocentric model, placing the sun at the center of the universe, and made the first known attempts to calculate the relative sizes and distances of the sun and moon. His work, however, was largely overshadowed by Aristotle's geocentric model, which dominated thought for nearly 2 millennia. The true revolution in solar observation began in the 16th and 17th centuries. Nicolaus Copernicus's heliocentric model, published posthumously in 1543, definitively shifted Earth from the center of the cosmos to a mere planet orbiting the sun. This paradigm shift opened the floodgates for new discoveries. It was Galileo Galilei who, in the early 17th century, turned his newly invented telescope towards the sun, though without proper protection, damaging his eyesight. He made groundbreaking observations of sunspots, the dark blemishes on the sun's surface. Crucially, he noted their movement, proving that the sun rotated on its axis, a stunning revelation that challenged the prevailing notion of perfect, unchanging celestial bodies. Around the same time, Christoph Scheiner and Johannes Fabricius also independently observed sunspots, further confirming these dynamic features. As technology advanced, so did our understanding. The invention of the spectroscope in the 19th century allowed scientists like Joseph von Fraunhofer and Gustav Kirchhoff to analyze the sun's light in unprecedented detail. They discovered thousands of dark lines in the solar spectrum, now known as Fraunhofer lines, which Kirchhoff theorized corresponded to specific chemical elements absorbing light in the sun's atmosphere. This discovery was monumental. It allowed astronomers to deduce the sun's composition, predominantly hydrogen and helium, without ever leaving Earth. The 20th century marked the dawn of modern astrophysics and the beginning of a truly deep understanding of the sun. Albert Einstein's theory of relativity, particularly his famous equation, E equals mc A, provided the theoretical framework for how stars could generate such immense energy through nuclear fusion. Later, Hans Bethe accurately described the proton-proton chain reaction, the specific fusion process occurring in the Sun's core, earning him the Nobel Prize in Physics. This journey of observation, from ancient reverence to modern scientific inquiry, highlights humanity's persistent quest to comprehend the most dominant object in our sky. We've moved from seeing a divine chariot to understanding a complex, dynamic star, a journey we continue to this day with increasingly sophisticated tools. In the vast expanse of this discussion, we will embark on a comprehensive exploration of our Sun. We will peel back its layers, from the unimaginably hot and dense core where nuclear fusion sparks to life, to the dynamic and mysterious corona that extends millions of kilometers into space. We will unravel the intricate dance of magnetic fields that drive its dramatic surface phenomena, from the dark allure of sunspots to the explosive power of solar flares and coronal mass ejections. Furthermore, we will delve into the profound and sometimes disruptive ways the Sun's activities impact our home planet, collectively known as space weather, influencing everything from dazzling aurorae to potential threats to our technology. We will also examine the ingenious tools and techniques astronomers employ, both on Earth and in space, to continuously monitor and decode the Sun's secrets. Finally, we will gaze far into the future, contemplating the ultimate fate of our Sun and its implications for Earth. Prepare to be amazed by the sheer power, complexity, and life-giving essence of the star we call our Sun. The Sun's grand architecture, layers from core to corona. To truly understand the Sun, we must peel back its fiery layers, much like an onion, to reveal the incredible physics at play within. While it appears as a solid, burning sphere from Earth, the Sun is actually a massive ball of plasma, a superheated state of matter where atoms are stripped of their electrons. This plasma is organized into distinct layers, each with unique characteristics and crucial roles in generating and transporting the Sun's immense energy. The core, the nuclear furnace. At the very heart of the Sun lies its core, a region of unimaginable extremes, extending out to about 20 to 25% of the Sun's total radius. The core is where all the magic happens, the place where the Sun as boundless energy is born. Extreme conditions. The conditions within the core are unlike anything we experience on Earth. Here, temperatures soar to an astonishing 15 million degrees Celsius, 27 million degrees Fahrenheit. The pressure is equally mind-boggling, estimated to be about 250 billion times greater than Earth's atmospheric pressure at sea level. This immense pressure, coupled with the extreme heat, results in an incredible density, about 150 times the density of water, meaning a spoonful of solar core material would weigh more than an average car. These conditions are absolutely essential for the processes that power the Sun, the proton-proton chain reaction. This is the specific set of nuclear fusion reactions that powers our Sun and other stars of similar mass. It's a multi-step process where hydrogen nuclei, protons, are ultimately fused together to form helium nuclei. Let's break down the primary steps. Step 1. Two protons, 1H, collide. One of them is converted into a neutron, and they fuse to form a deuterium nucleus 2H, releasing a positron E+, and an electron neutrino nu E p plus p gives D plus E plus plus nu E. The positron quickly encounters an electron, annihilating both particles and releasing energy in the form of gamma rays, gamma, E+. Plus E gives to gamma step 2. The newly formed deuterium nucleus then fuses with another proton to create a light helium nucleus 3, He, releasing another gamma ray. D plus P gives 3, He plus gamma step 3. This is the most common path, about 85% of the time. Two light helium nuclei 3, He collide, and fuse to form a stable helium-4 nucleus for He, releasing two protons in the process. These protons can then go back into the fusion cycle. 3, He plus 3, He gives 4, He plus 2. P. The net result of this entire chain reaction is that 4 hydrogen nuclei are converted into one helium-4 nucleus, a positron, 2 neutrinos, and a tremendous amount of energy in the form of gamma-ray photons and kinetic energy of the particles. It's this conversion of mass into energy, governed by Einstein's EMC2, that fuels the Sun's persistent glow. Every second, roughly 600 million tons of hydrogen are converted into helium. with about 4 million tons of that mass being directly transformed into pure energy. Neutrino production. One fascinating byproduct of the proton-proton chain is the immense number of neutrinos produced. These subatomic particles are often called ghost particles because they interact very weakly with matter. They fly straight out of the sun's core at nearly the speed of light, carrying direct information about the nuclear reactions happening deep within. Billions of solar neutrinos pass through your body every second, completely unnoticed. Detecting these elusive particles on Earth has provided crucial confirmation of our models of solar fusion. Hydrostatic equilibrium. The sun doesn't collapse under its own immense gravity because of a delicate balance known as hydrostatic equilibrium. The outward pressure generated by the hot gas and the continuous nuclear fusion in the core precisely counteracts the inward pull of gravity from the sun's enormous mass. This balance is what keeps the sun stable and shining steadily for billions of years. If fusion slowed, gravity would win, causing the sun to contract and heat up, which would then restart fusion. If fusion sped up, the sun would expand and cool, slowing fusion down. This self-regulating mechanism ensures long-term stability. The radiative zone, a journey of photons. Just outside the core lies the radiative zone, extending from about 25% to 70% of the sun's radius. This layer is a dense, scorching hot region where energy transport primarily occurs through radiation. Mechanism of energy transport. Unlike the turbulent core or the boiling convective zone, the radiative zone is relatively calm. Energy generated in the core, primarily in the form of high-energy gamma-ray photons, tries to make its way outwards. However, the plasma in this zone is incredibly dense and opaque. These photons don't travel in a straight line. Instead, they are constantly absorbed and re-emitted by atoms and ions. Imagine trying to walk through a dense crowd where every few steps you bump into someone, stop, and then change direction. That's essentially the journey of a photon in the radiative zone. The incredibly long random walk. This continuous process of absorption and re-emission means that a single photon can take an extraordinarily long time to traverse the radiative zone. Estimates suggest it can take anywhere from 100,000 to several million years for a photon to complete this random walk from the core to the top of the radiative zone. By the time it finally emerges, its energy has been significantly degraded from high-energy gamma rays into lower-energy X-rays and ultraviolet radiation. As it interacts with the plasma, this incredibly slow outward migration of energy highlights the sheer density and opacity of this solar layer. Distinct properties. The radiative zone is characterized by its high temperature and density, but also by a lack of significant mass movement, convection. The energy transfer is dominated by photon transport. This contrasts sharply with the convective zone above it, where physical movement of plasma is the primary mode of energy transfer. The boundary between the radiative zone and the convective zone is known as the tachyon line, a region of strong shear where the sun has differential rotation, different parts rotating at different speeds, is thought to be crucial for generating the sun's magnetic field. The convective zone, boiling plasma. The outermost layer of the sun's interior is the convective zone, stretching from about 70% of the sun's radius all the way to its visible surface, the photosphere. This is where energy finally makes its grand exit to the surface through a process similar to boiling water. Mechanism of energy transport. Convection cells. In this zone, the plasma is cooler and less dense than in the radiative zone, allowing for a different form of energy transport. Convection. Hotter, less dense plasma, near the bottom of the convective zone, rises towards the surface, carrying energy with it. As it approaches the cooler surface, it releases its heat, cools down, becomes denser, and then sinks back down to be reheated, creating a continuous cycle of rising and falling currents, much like the circulation in a boiling pot of water or a lava lamp. Granulation and supergranulation. We can actually see the top of these convection cells on the sun's visible surface as a pattern called granulation. The boundary with the radiative zone. The transition from the radiative zone to the convective zone marks a fundamental shift in how energy moves through the sun. This turbulent, churning region plays a critical role in bringing the enormous energy generated in the core to the sun's surface, ready to radiate out into space and reach our distant Earth. The differential rotation of the Sun, where the equator rotates faster than the poles, is particularly pronounced within the convective zone and the Tachak line. And this shear is absolutely vital for generating the Sun's powerful magnetic field, which in turn drives all the spectacular phenomena we see on its surface and in its atmosphere. The photosphere, the visible surface. When we look at the Sun, what we are actually seeing is the photosphere. This is not a solid surface like Earth's, but rather a thin layer of gas, about 500 kilometers, 300 miles, thick, that defines the boundary where the Sun's plasma becomes transparent enough for light to escape into space. Definition and what makes it visible. The term photosphere literally means sphere of light. It's the layer from which most of the Sun's visible light is emitted. Below this layer, the plasma is too dense and opaque for photons to travel freely. Above it, the plasma becomes too tenuous to emit much visible light. So, the photosphere is essentially the skin of the Sun that we can directly observe. Temperature gradients and limb darkening effect. The temperature of the photosphere isn't uniform. Spectra of the photosphere, absorption lines, and chemical composition. One of the most significant pieces of information we get from the photosphere comes from analyzing its light through a spectrum. The continuous spectrum of light emitted from the deeper, hotter parts of the photosphere passes through the cooler gases in the upper photosphere. Specific elements in these cooler gases absorb light at particular wavelengths, creating dark lines in the spectrum known as Fraunhofer lines. Each element leaves a unique fingerprint of these absorption lines. By studying these lines, scientists were able to determine the Sun's chemical composition, confirming that it is predominantly made of hydrogen, about 74% by mass, and helium, about 24% by mass, with trace amounts of heavier elements like oxygen, carbon, neon, iron, and nitrogen. This technique revolutionized astrophysics, allowing us to understand the composition of stars across the universe. The chromosphere, a dynamic middle layer. Above the brilliant photosphere lies the chromosphere, a relatively thin and irregular layer of gas, extending for about 2,000 to 3,000 kilometers, 1,200 to 1,900 miles. Its name, meaning sphere of color, comes from its characteristic reddish glow, which is only visible to the naked eye during a total solar eclipse, when the bright photosphere is blocked. Normally, its faint light is overwhelmed by the glare of the photosphere. How it's observed: H-alpha, Ka, to K-line. To observe the chromosphere outside of an eclipse, astronomers use specialized filters that block most of the Sun's light and only allow specific wavelengths to pass through. The most common filter is the H-alpha filter, which isolates the deep red light emitted by hydrogen atoms at 656.3 nanometers. Another important filter is the Ka2 K-line filter, which shows light from ionized calcium. These filters reveal the chromosphere's dynamic structures that are invisible in white light: spicules, fibrils, and magnetic heating. The chromosphere is not a smooth, uniform layer. It's a turbulent region filled with various short-lived, dynamic features. The most prominent are spiculous, thin, jet-like structures of plasma that shoot upwards from the photosphere into the chromosphere, reaching heights of up to 10,000 kilometers, 6,200 miles, and lasting only about 5 to 15 minutes before collapsing. They look like tiny blades of grass covering the Sun. Similarly, fibrils are longer, darker, thread-like structures that follow magnetic field lines. The chromosphere is hotter than the photosphere, reaching temperatures of up to 20,000 degrees Celsius, 36,000 degrees Fahrenheit, at its top. This counterintuitive increase in temperature as you move away from the core is a long-standing puzzle known as the chromospheric heating problem. Scientists believe it's primarily caused by the dissipation of magnetic waves and reconnection events that funnel energy into this layer, the corona, the Sun's enigmatic outer atmosphere. The outermost and most expansive layer of the Sun's atmosphere is the corona. This ethereal, pearly white halo extends millions of kilometers or miles into space, far beyond the visible disk of the Sun. Like the chromosphere, it's typically only visible during a total solar eclipse, or with specialized instruments called coronagraphs that artificially block out the blinding light of the photosphere. Extreme temperatures and low density. The most striking feature of the corona is its incredibly high temperature. which can exceed 1 million degrees Celsius, 1.8 million degrees Fahrenheit, sometimes even reaching several tens of millions of degrees. This is astonishingly hot, especially when compared to the relatively cool 5,500 degrees Celsius of the photosphere. This extreme heat has been one of the biggest mysteries in solar physics, known as the coronal heating problem. Despite its extreme temperature, the corona is incredibly tenuous, with a density millions of times lower than the Earth's atmosphere at sea level. This low density is why it's so faint and hard to see, and also why astronauts passing through it wouldn't feel the heat in the same way they would in a dense hot oven. Coronal heating problem. Current theories. The fact that the corona is so much hotter than the layers below it is a major scientific puzzle. The sun's energy flows outwards, so intuitively, the further away from the core you go, the cooler it should get. Many theories have been proposed to explain this inverse temperature gradient, with the leading candidates involving the sun's powerful magnetic field. Magnetic reconnection. This theory suggests that magnetic field lines in the corona twist, tangle, and then suddenly reconnect, releasing vast amounts of energy in explosive bursts. These microflares or nanoflares could collectively heat the corona. Waves. Another prominent theory posits that waves of plasma and magnetic field, called waves, are generated by the turbulent motion in the convective zone and propagate upwards. These waves then dissipate their energy in the corona, converting it into heat. It's likely a combination of these and other mechanisms that contribute to the coronal heating. Coronal holes and their connection to solar wind. The corona is not uniform. Observations, particularly in X-ray and UV wavelengths, reveal regions called coronal holes. These are darker, cooler, and less dense areas in the corona where the sun's magnetic field lines are open, meaning they extend outwards into interplanetary space rather than looping back down to the sun's surface. These open field lines act like nozzles, allowing the sun's plasma to stream out freely at high speeds, forming the solar wind. Coronal holes are therefore the primary source of the high-speed solar wind. This detailed look into the sun's layered structure provides the fundamental framework for understanding how our star produces and transports energy, ultimately setting the stage for the dramatic surface activities and space weather phenomena we'll explore next. The sun's dynamic activity, a symphony of magnetism. Beyond its layered structure, the sun is a powerhouse of activity, constantly churning and flexing. This isn't just random turbulence. It's a meticulously choreographed symphony driven by the sun's incredibly powerful and complex magnetic field. This magnetic field is the architect behind all the dramatic phenomena we observe on the sun's surface and in its atmosphere, from dark sunspots to colossal explosions that can reach Earth. Unlike Earth, which has a solid core acting like a giant bar magnet, the sun's magnetic field is generated by the movement of its electrically charged plasma. This process is known as the solar dynamo. Origin of the magnetic field. The solar dynamo, the sun's dynamo, is primarily powered by two key factors within its interior: convection, the turbulent, boiling motions of plasma in the convective zone, stretch and twist, magnetic field lines. Imagine kneading dough. The movements within the dough will stretch and fold any lines embedded within it. Differential rotation. The sun does not rotate as a solid body. Its equator rotates faster once every approximately 25 days than its poles once every approximately 35 days. This differential rotation causes the magnetic field lines that initially run north-south to get stretched and wound up around the sun's equator, like rubber bands wrapping around a spinning ball. This stretching intensifies the magnetic field lines, making them stronger. This combination of convection and differential rotation creates a self-sustaining cycle where magnetic fields are continuously generated, amplified, and transported, creating the sun's global magnetic field. The region where this process is most active is thought to be the Tachak line, the interface between the radiative and convective zones, magnetic flux tubes, and their behavior. The sun's magnetic field isn't uniform. It often forms concentrated bundles of magnetic field lines, known as magnetic flux tubes. These tubes can become so strong and buoyant that they push their way up from beneath the surface, breaching the photosphere and creating visible features. Where these flux tubes emerge and loop back into the sun, They form regions of intense magnetic activity. Hale's polarity law and the Babcock-Lytton dynamo model. The Sun's magnetic field reverses its polarity approximately every 11 years, marking the beginning of a new solar cycle. This systematic behavior is described by Hale's polarity law, which states that sunspots in the leading part of a sunspot pair in one hemisphere have the same magnetic polarity which is opposite to the polarity of sunspots in the other hemisphere. In the next solar cycle, these polarities reverse. This observation was crucial in developing the Babcock-Lytton dynamo model, a leading theory that explains how the Sun's magnetic field is generated and how its polarity systematically reverses over the 22-year magnetic cycle to 11-year sunspot cycles. This model involves the transport of magnetic flux from decaying sunspots to the poles, where it eventually contributes to the reversal of the global magnetic field. The most easily observable manifestation of the Sun's powerful magnetic field are sunspots. These dark patches on the photosphere have fascinated observers since Galileo's time, and their appearance signals regions of intense magnetic activity. Detailed anatomy, umbra and penumbra. A typical large sunspot consists of two main parts. Umbra, the central darkest region, which is the coolest part of the sunspot, typically around 3,500 degrees Celsius, 6,300 degrees Fahrenheit. Penumbra, a lighter filamentary region surrounding the umbra, where temperatures are slightly higher, but still cooler than the surrounding photosphere. The penumbral filaments are thought to be channels where magnetic fields allow gas to flow. The reason sunspots appear dark is simply because they are cooler than the surrounding photosphere, which is about 5,500 degrees Celsius. Even though they are still incredibly hot, this temperature difference makes them appear dark. By contrast, how sunspots are formed and their magnetic structure. Sunspots form when strong magnetic flux tubes from the Sun's interior become so concentrated and buoyant that they punch through the photosphere. The intense magnetic field within these regions inhibits the normal convection of hot plasma from below. This suppression of heat flow means that the gas in the sunspot cools down, making it appear darker. Sunspots almost always appear in pairs or groups, with opposite magnetic polarities, indicating that they are the two ends of a magnetic loop emerging from and re-entering the Sun. The Schwabe cycle 11-year solar cycle. Perhaps the most remarkable aspect of sunspots is their cyclical nature. The number of sunspots visible on the Sun varies over an approximately 11-year cycle, known as the Schwabe cycle, named after Heinrich Schwabe, who first systematically observed it. Solar minimum. At the beginning of a cycle, solar minimum, very few sunspots are present, and those that do appear are typically found at higher solar latitudes around 30-35 degrees. Solar maximum. As the cycle progresses, the number of sunspots increases, and they tend to appear closer to the Sun's equator, around 15 degrees. This period of peak sunspot activity is called solar maximum. Solar minimum again. The number of sunspots then declines again, moving towards the equator, until the next solar minimum. This pattern can be visualized using a butterfly diagram, which plots the latitude of sunspots over time, creating a butterfly wing shape. This 11-year cycle in sunspot number is a direct manifestation of the underlying 22-year magnetic cycle of the solar dynamo, as the magnetic fields systematically build up, emerge, and then reverse polarity. Historically, there have been periods of exceptionally low sunspot activity, such as the Maunder minimum 1645 to 1715, when very few sunspots were observed. This period coincided with a colder climate on Earth, sparking debate about the Sun's long-term influence on our planet's climate. Sunspots are often the precursors to some of the most spectacular and energetic events in the solar system. Solar flares. Mechanism. Magnetic reconnection. Solar flares are sudden, intense bursts of radiation that occur when magnetic field lines in the Sun's atmosphere, often above sunspot regions, become tangled, twisted, and stressed. When these stressed magnetic field lines abruptly snap and reorganize into a simpler, lower-energy configuration, this process, called magnetic reconnection, releases an enormous amount of stored magnetic energy. This energy rapidly heats plasma to tens of millions of degrees, accelerating charged particles to near light speed, and producing a broad spectrum of electromagnetic radiation. Classification XMC, B classes, and energy release. Solar flares are classified by their peak X-ray brightness, measured by satellites like the Geostationary Operational Environmental Satellite Series. The classifications are exponential, with each class being 10 times more powerful than the one below it. X-class flares, the largest and most intense flares, capable of causing widespread radio blackouts and significant space weather effects. M-class flares, medium-sized flares, capable of causing minor radio blackouts. C-class flares, small flares, with few noticeable effects on Earth. B-class and A-class flares, even smaller background flares. The energy released by a large X-class flare can be equivalent to millions of hydrogen bombs exploding simultaneously, all within a matter of minutes. This energy is emitted across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. Electromagnetic spectrum of flares. The radiation from a solar flare travels at the speed of light, reaching Earth in about 8 minutes. Different wavelengths tell us about different processes. X-rays and extreme ultraviolet EUV. These high-energy photons are produced by the extremely hot plasma during the flare. They are quickly absorbed by Earth's upper atmosphere, ionosphere, causing sudden ionization, which can lead to radio blackouts. Visible light and H-alpha. Flares can also be seen in visible light, though they are much less spectacular than their X-ray counterparts. H-alpha filters, for instance, highlight the energetic hydrogen emissions during a flare. Radio waves. Flares also generate bursts of radio waves, which can interfere with terrestrial communications and navigation systems. While solar flares are bursts of radiation, coronal mass ejections, CMEs, are massive expulsions of the sun's plasma and magnetic field into space. They are essentially giant burps of material from the sun's outer atmosphere, the corona. Formation and propagation. CMEs often originate from regions where the magnetic field lines in the corona are highly stressed and tangled, similar to solar flares. In fact, many powerful solar flares are accompanied by CMEs, although they are distinct phenomena. A flare is a burst of light. A CME is a burst of mass. When the magnetic field lines reconfigure, they can propel vast amounts of coronal plasma, sometimes billions of tons of material, outwards into the solar system. CMEs can travel at speeds ranging from a few hundred kilometers per second to over 3,000 kilometers per second, nearly 7 million miles per hour. Types of CMEs and their speeds. CMEs are not all uniform. Some are relatively slow and broad, while others are fast and narrow. The speed and direction of ACME are crucial for determining its potential impact on Earth. Faster CMEs tend to be more energetic and can cause more significant space weather effects. The magnetic field embedded within the CME, particularly its orientation relative to Earth's magnetic field, is also a critical factor. Relationship between CMEs and solar flares. While CMEs and solar flares are distinct, they are often observed together and are both driven by the same fundamental process: the sudden release of magnetic energy in the sun's corona. It's often said that a solar flare is like a flashbulb, emitting light, while a CME is like the shotgun blast, expelling mass. Not every flare has a CME, and not every CME is associated with a bright flare. But the most powerful events typically involve both. The combination of intense radiation from a flare and the arrival of a massive plasma cloud from ACME can create significant space weather events. Among the visually stunning features on the sun are prominences and filaments. These are not explosions, but rather dense, cooler clouds of plasma suspended above the sun's surface by powerful magnetic fields. How they are formed and sustained by magnetic fields. Prominences form when dense, quiescent versus heat-up deep. Prominences can be broadly categorized into two types. Quiescent prominences. These are relatively stable and can persist for days or even months, often forming along magnetic shear lines where magnetic fields change direction. Eruptive prominences. These are unstable and can suddenly become active, rising rapidly and breaking away from the sun, often associated with CMEs. These eruptions contribute to the outflow of solar material into space. Their role in the solar atmosphere, prominences and filaments, provide crucial insights into the configuration and dynamics of the sun's magnetic field in the lower corona. They act as visible tracers of these complex magnetic structures, helping scientists understand how the sun's magnetic field traps and releases plasma. Beyond the dramatic eruptions, the sun is continuously shedding material in a steady stream of charged particles known as the solar wind. This constant outflow fills our entire solar system. Origin from coronal holes. The solar wind originates primarily from coronal holes, those darker, cooler, and less dense regions in the corona that we discussed earlier. In these areas, the sun's magnetic field lines are open. They extend outwards into interplanetary space, rather than looping back. This configuration allows plasma from the corona to escape freely along these open field lines, accelerating to high speeds. Fast and slow solar wind. The solar wind comes in two main forms. Fast solar wind originates from coronal holes, particularly at the sun's poles, and travels at speeds around 750 kilometers per second, about 1.7 million miles per hour. It's typically less dense and more uniform. Slow solar wind originates from the sun's equatorial regions and streamers, dense structures in the corona, and is slower, around 300 to 500 kilometers per second, but more variable and turbulent. The solar wind carries the sun's magnetic field with it, forming the interplanetary magnetic field IMF, which spirals outwards due to the sun's rotation. Interaction with planetary magnetospheres. The solar wind constantly streams past all the planets in our solar system. For planets with strong global magnetic fields, like Earth, the solar wind is largely deflected by the magnetosphere, creating a protective bubble around the planet. For planets without significant magnetic fields, like Mars or Venus, the solar wind interacts directly with their upper atmospheres, stripping away atmospheric gases over geological timescales. The interaction of the solar wind with Earth's magnetosphere is the primary driver of space weather, which we will explore in the next section. The sun's constant activity isn't just a spectacle. It has profound and often tangible effects throughout the solar system, particularly on Earth. This interaction between the sun and our planet's environment is known as space weather, unlike terrestrial weather, which deals with conditions in Earth's lower atmosphere. Space weather refers to the variable conditions on the sun and in the space environment, which can influence the performance and reliability of spaceborne and ground-based technological systems, and even endanger human life or health. Before delving into the impacts of space weather, it's crucial to understand Earth's primary defense mechanism, its magnetosphere. This is a vast, invisible magnetic bubble that surrounds our planet, generated by the convective motion of molten iron in Earth's outer core. How Earth's magnetic field protects us. The magnetosphere acts like a giant shield, deflecting most of the charged particles plasma, streaming out from the sun, in the solar wind, and from more extreme events, like CME. Without this protective bubble, the solar wind would directly strip away Earth's atmosphere, making our planet uninhabitable, much like what is thought to have happened to Mars over billions of years. The bow shock, magnetopause, and magnetail. As the supersonic solar wind slams into Earth's magnetosphere, it creates a bow shock, a region where the solar wind abruptly slows down and becomes turbulent. The outer boundary of the magnetosphere, where the solar wind pressure is balanced by the internal magnetic pressure of Earth's field, is called the on the side of Earth, facing away from the sun. The solar wind stretches the magnetosphere into a long, comet-like structure, called the magnetail, extending millions of kilometers into space. This magnetail stores enormous amounts of magnetic energy, which can be released in spectacular fashion. The most dramatic manifestation of space weather is a geomagnetic storm, a major disturbance of Earth's magnetosphere. These storms occur when a powerful CME, or a prolonged stream of high-speed solar wind, from a coronal hole impacts Earth's magnetic field. How CMEs and solar wind interact with the magnetosphere. When a CME, carrying its own embedded magnetic field, the Interplanetary Magnetic Field, or IMF, arrives at Earth, its interaction with Earth's magnetosphere is critical. If the IMF's magnetic field is oriented southward, opposite to Earth's northward magnetic field, it can reconnect with Earth's field lines. This magnetic reconnection process allows energy and plasma from the solar wind to be effectively transferred into Earth's magnetosphere, leading to a massive redistribution of energy and particles within the magnetosphere and ionosphere. This influx of energy drives geomagnetic storms, DST index, and storm intensity. The intensity of a geomagnetic storm is typically measured by the DST disturbance, storm time index, which quantifies the horizontal component of the geomagnetic field at the magnetic equator. A more negative DST value indicates a stronger storm. Geomagnetic storms are classified from G1 minor to G5, extreme based on their potential impact, corresponding to varying DST values. Historical geomagnetic storms. The Carrington event of 1859. This is considered the most powerful geomagnetic storm in recorded history. On September 1st to 2nd, 1859, a massive solar flare observed by Richard Carrington was followed by a fast-moving CME that struck Earth. The resulting geomagnetic storm caused widespread disruptions to the nascent telegraph systems, delivering electric shocks to operators and even setting telegraph papers on fire. Aurorae were so bright they were seen as far south as the Caribbean. Had this event occurred today, its impact on our technology-dependent society would be catastrophic. The Quebec blackout of 1989. A less extreme, but still significant. Geomagnetic storm occurred on March 13, 1989. A strong CME hit Earth, inducing currents in the power grid of Quebec, Canada. Within minutes, the entire hydropower system collapsed, leaving 6 million people without electricity for up to 9 hours. This event served as a stark reminder of our vulnerability to space weather. The sun's X-ray and UV radiation, especially during solar flares, directly impacts Earth's ionosphere, a region of the upper atmosphere containing electrically charged particles. Sudden ionospheric disturbances SIDS, from X-rays, when a powerful solar flare erupts. Its X-ray radiation reaches Earth in about 8 minutes. These X-rays cause a sudden and dramatic increase in the ionization of the dirigion of the ionosphere, the lowest layer. This increased ionization leads to a sudden increase in radio wave absorption, effectively causing sudden ionospheric disturbances, SIDS. Impact on HF radio, GPS, and satellite communications. SIDs primarily affect high-frequency, HF radio communications, which rely on the ionosphere to reflect radio waves over long distances. During an SID, these signals can be absorbed instead of reflected, leading to immediate and widespread radio blackouts. This can impact aviation, maritime communications, and amateur radio operators. More severe disturbances, often associated with CMEs, can also affect GPS global positioning system signals. GPS signals travel through the ionosphere. An increased ionization can cause delays and errors in positioning accuracy, affecting everything from precision agriculture to navigation. Satellite communications, particularly those using higher frequencies, can also experience signal degradation or outages during intense space weather events. One of the most concerning impacts of severe geomagnetic storms is their potential to disrupt terrestrial power grids. Mechanism of GICs, geomagnetically induced currents. During a geomagnetic storm, the rapid fluctuations in Earth's magnetic field induce electric currents in long conductors on the ground, such as pipelines, railway lines, and most critically, power transmission lines. These are called geomagnetically induced currents, GICs. Because power grids are interconnected over vast distances, GICs can enter the transformers that step up and step down voltage. Vulnerability of long transmission lines. Transformers are not designed to handle these direct currents, DCS, superimposed on their normal alternating current AC operation. The DC component causes the transformer cores to saturate, leading to harmonic distortions, voltage sags, and increased reactive power draw. This can cause transformers to overheat and, in severe cases, be permanently damaged or even trip safety mechanisms, leading to widespread power outages. As seen in Quebec in 1989, modern power grids are increasingly interconnected and reliant on long transmission lines, potentially increasing their vulnerability to extreme GICs. Satellites in orbit and astronauts in space are directly exposed to the space environment, making them particularly vulnerable to solar activity. Radiation hazards for spacecraft, electronics, and human spaceflight. Solar energetic particles SEPs, solar flares and CMEs can accelerate particles, protons, electrons, heavy ions, two very high energies, forming solar energetic particle SEP events. These SEPs can penetrate spacecraft shielding and cause damage to sensitive electronic components, leading to single event upsets SEUs, or even permanent damage. Astronaut safety. For astronauts, especially those on long-duration missions outside the protection of Earth's magnetosphere, like a future mission to Mars, SEPs pose a severe radiation hazard. High doses of radiation can cause acute radiation sickness, increase the risk of cancer, and damage DNA. Missions need robust shielding and effective warning systems to allow astronauts to take shelter. Atmospheric drag on low Earth orbit satellites. During periods of high solar activity, solar maximum, the Sun's increased UV and X-ray radiation heats Earth's upper atmosphere, causing it to expand. This expansion increases the density of the atmosphere at the altitudes where many low Earth orbit LEO satellites operate. The increased atmospheric drag on these satellites can cause them to slow down, drop to lower orbits, and potentially re-enter the atmosphere prematurely. Satellite operators must constantly monitor solar activity and periodically boost their satellites to higher orbits to counteract this effect, which consumes valuable fuel and shortens satellite lifespan. One of the most beautiful and visible effects of space weather is the aurora, the stunning light display in the polar skies. Physics behind aurora formation. Aurorae occur when charged particles from the solar wind or from geomagnetic storms are channeled along Earth's magnetic field lines towards the magnetic poles. As these energetic particles collide with atoms and molecules in Earth's upper atmosphere, primarily oxygen and nitrogen, they excite these atmospheric gases. When the excited atoms and molecules de-excite, they emit light at specific wavelengths, creating the vibrant colors of the aurora. Colors of the aurora, an atmospheric composition. The color of the aurora depends on the type of gas being excited and the altitude at which the collisions occur. Green, the most common color, produced by oxygen atoms at altitudes of about 100 to 300 kilometers, 6,180 miles. Red, produced by oxygen atoms at higher altitudes above 300 kilometers, or by nitrogen molecules at lower altitudes. Blue, purple, produced by nitrogen molecules and ions at lower altitudes below 100 kilometers. The more intense the solar activity, the more energetic the particles, and the further away from the poles the aurora can be seen, sometimes extending to mid-latitudes during powerful geomagnetic storms. Beyond the short-term impacts of space weather, there's a fascinating and complex question about the Sun's long-term influence on Earth's climate. The Sun's influence on Earth's climate, for example, solar irradiance, cosmic rays, the Sun's energy output, known as total solar irradiance, TSI, varies slightly over the 11-year solar cycle, with about a 0.1% increase from solar minimum to maximum. While this variation is small, some scientists explore whether these subtle changes, along with other solar phenomena, could influence Earth's climate. Other factors include ultraviolet, UV radiation. UV radiation varies more significantly than total solar irradiance and can impact the ozone layer and atmospheric chemistry, potentially affecting atmospheric circulation patterns. Cosmic rays. The Sun's magnetic field and the solar wind create a protective bubble, the heliosphere, that partially shields Earth from galactic cosmic rays. During periods of high solar activity, the heliosphere expands, providing more shielding and reducing the influx of cosmic rays. Some theories suggest that variations in cosmic rays could influence cloud formation on Earth, though this remains a subject of active research and debate. Discussing the potential link between solar minima and historical cold periods. Historical records show correlations between periods of prolonged low solar activity, such as the Maunder, minimum 1645 to 1715, and colder periods on Earth, like parts of the Little Ice Age. While intriguing, the exact mechanism and the extent to which solar variability contributes to long-term climate change compared to other factors, like volcanic activity or greenhouse gas concentrations, is a complex area of scientific research. The scientific consensus is that while solar variability does play a role in Earth's climate, its contribution to the recent rapid warming observed over the last century is significantly less than that of human-caused greenhouse gas emissions. Understanding space weather is not just an academic exercise. It's a vital field of research for protecting our modern technology-dependent society, from ensuring reliable communication and navigation to safeguarding power grids and astronauts. Monitoring and predicting the sun's behavior has become paramount. Our profound understanding of the sun, from its nuclear core to its far-reaching solar wind, isn't derived from guesswork. It's the result of centuries of relentless observation, coupled with the development of increasingly sophisticated tools. Modern solar astronomy combines powerful telescopes on Earth with an armada of specialized spacecraft, each designed to capture different facets of our star's complex behavior. While Earth's atmosphere presents challenges for clear astronomical viewing, ground-based solar observatories remain indispensable, often providing unparalleled resolution and long-term datasets. Solar telescopes, for example, Daniel K. Inouye Solar Telescope, DKIST, Big Bear Solar Observatory, BBSO. Unlike nighttime optical telescopes, designed to gather faint light from distant galaxies, solar telescopes are built to handle the intense brightness and heat of the sun. They employ specialized optics and cooling systems to safely focus sunlight for study. DKIST, Daniel K. Inouye Solar Telescope. Located atop Haleakala, Hawaii, DKIST is currently the world's largest solar telescope. Its massive 4-meter primary mirror allows it to achieve unprecedented resolution, capable of viewing features on the sun's surface as small as 20 kilometers, 12 miles across. This has revolutionized our ability to study granulation, sunspots, and magnetic fields in exquisite detail, providing crucial data for understanding the solar dynamo and coronal heating. BBSO, Big Bear Solar Observatory, situated on an island in Big Bear Lake, California. BBSO benefits from excellent seeing conditions due to the surrounding water, which stabilizes the air. It specializes in high-resolution observations of solar activity, using adaptive optics to correct for atmospheric distortions and provide incredibly sharp images of sunspots, flares, and prominences. Spectrographs, magnetographs, and coronagraphs. Solar observatories don't just take pretty pictures. They employ a suite of instruments to analyze the sun's light in detail. Spectrographs. These instruments disperse light into its constituent wavelengths, creating a spectrum. By analyzing the Fraunhofer lines, absorption lines, in the solar spectrum, astronomers can determine the sun's chemical composition, temperature, density, and even the velocity of gases via the Doppler effect. This is how we know what the sun is made of, and how quickly different parts of its surface are moving. Magnetographs. These specialized instruments measure the strength and direction of the sun's magnetic fields. They do this by exploiting the Zeeman effect, where the presence of a magnetic field causes spectral lines to split into multiple components. By analyzing these splits, magnetographs can map the complex magnetic architecture of the sun's photosphere and chromosphere, revealing the intricate patterns of sunspots and active regions. Coronagraphs. To view the faint corona from Earth's surface, outside of a total solar eclipse, coronagraphs are essential. These instruments use an opaque disk to block out the blinding light from the sun's photosphere, much like the moon does during an eclipse. This allows the much fainter corona to become visible for continuous study, revealing its dynamic structures and outflow of plasma. Adaptive optics for clearer views. A major challenge for ground-based telescopes is the blurring effect of Earth's turbulent atmosphere. Adaptive optics AO systems overcome this by using rapidly deforming mirrors that adjust their shape hundreds or thousands of times per second. These mirrors compensate for atmospheric distortions in real time, allowing telescopes to capture images that are nearly as sharp as those from space. This technology has dramatically improved the resolution of ground-based solar observations. To overcome the limitations of Earth's atmosphere, which absorbs most high-energy radiation like X-rays and UV, and distorts visible light, scientists deploy a fleet of specialized spacecraft. These missions offer uninterrupted views of the sun and can observe it across the entire electromagnetic spectrum. SOHO, Solar and Heliospheric Observatory, a joint mission between NASA and ESA. SOHO was launched in 1995 and has been an incredibly successful and long-lived solar observatory. Positioned at the L1 Lagrangian point, a gravitationally stable point between Earth and the Sun, SOHO enjoys a continuous, unobstructed view of the Sun. Its multi-instrument approach includes coronagraphs, providing constant views of the corona and detecting CMEs as they erupt; spectrometers, analyzing the composition and temperature of the solar wind and atmosphere; helioseismology instruments, studying the sun's interior by detecting oscillations, sound waves, on its surface, much like seismologists study Earth's interior using earthquakes. SOHO has revolutionized our understanding of the sun's interior, its outer atmosphere, and the origin of the solar wind. It's also played a crucial role in space weather forecasting by detecting CMEs heading towards Earth. SDO Solar Dynamics Observatory, launched by NASA in 2010. SDO is designed to study the sun's influence on Earth and space. It provides incredibly high-resolution images and data of the sun's entire disk and atmosphere simultaneously, across multiple wavelengths, almost in real time. High-resolution imaging (SDOs), atmospheric imaging assembly, IA captures full disk images of the sun, in various ultraviolet and extreme ultraviolet wavelengths, every 12 seconds, revealing the dynamic nature of the chromosphere and corona. Real-time data. SDO's continuous stream of data is vital for space weather prediction, allowing scientists to observe flares and CMEs as they happen. Its data helps us understand the mechanisms behind solar activity and their impact on Earth. SDO has provided breathtaking videos of solar flares, prominences, and magnetic loops, making solar physics more accessible and visually stunning than ever before. Parker Solar Probe. Launched by NASA in 2018, the Parker Solar Probe is on a groundbreaking mission to literally touch the sun. Touching the sun, its primary goals are to understand how the sun's corona is heated to such extreme temperatures, the coronal heating problem, and to investigate the origin and acceleration mechanisms of the solar wind. By directly sampling the solar wind and magnetic fields at their source, Parker Solar Probe provides crucial insight to measurements that cannot be obtained from Earth's orbit. Measuring solar wind and magnetic fields up close. Equipped with a revolutionary heat shield and sophisticated instruments, the probe is collecting data on the sun's magnetic field, electric fields, plasma density, temperature, and the composition of the solar wind, offering unprecedented insights into our star's most active regions. Solar Orbiter, a joint mission between ESA and NASA. Solar Orbiter was launched in 2020. Its unique elliptical orbit allows it to travel closer to the sun. Studying the sun's poles, a key feature of Solar Orbiter is its ability to gradually increase its orbital inclination, allowing it to image the sun's poles for the first time. The polar regions are crucial for understanding the solar dynamo and the origin of the fast solar wind, but they are difficult to observe from Earth's ecliptic plane. Studying space weather, Solar Orbiter carries both remote sensing instruments to take images of the sun and in situ instruments to measure the space environment it flies through, providing a comprehensive view of the connections between what happens on the sun and the space weather conditions it creates. Other notable missions, for example, Stereo Hinode. The Solar Observation Fleet also includes other vital missions. Stereo Solar Terrestrial Relations Observatory consists of 2 spacecraft that orbit the sun, one ahead of Earth and one behind, providing a stereoscopic 3D view of the sun and CMEs. This eyesight is critical for predicting whether Acme is heading towards Earth. Hinode, formerly Solar B, a Japanese-led mission with international collaboration, provides high-resolution observations of the sun's magnetic field and its dynamic atmosphere, helping to understand magnetic reconnection and energy release. While all the above missions observe photons or charged particles, a very different kind of observatory is dedicated to studying the sun's deepest interior. Neutrino Observatorius, detecting neutrinos from the sun's core. As we discussed in Section 2, the nuclear fusion reactions in the sun's core produce an immense number of neutrinos. Because neutrinos interact so weakly with matter, they escape the sun's core almost immediately and travel unimpeded through the sun's dense layers and straight through Earth. The solar neutrino problem and its resolution neutrino oscillation. For decades, scientists observed fewer solar neutrinos reaching Earth than predicted by solar models. This discrepancy was known as the solar neutrino problem. It led to 2 main possibilities. Either our models of the sun's interior were wrong, or our understanding of neutrinos was incomplete. The mystery was finally resolved in the late 1990s and early 2000s by experiments like the Sudbury Neutrino Observatory SNO in Canada. These experiments confirmed that neutrinos have a tiny amount of mass and can oscillate or change between different flavors, electron, muon, and tau neutrinos, as they travel from the Sun to Earth. Since earlier detectors were only sensitive to electron neutrinos, the type produced in the Sun, they were missing the other flavors. This discovery not only solved the solar neutrino problem, but also provided crucial evidence for physics beyond the standard model of particle physics, confirming our understanding of the Sun's core processes. The synergy between ground-based observatories, with their high-resolution views and continuous long-term monitoring, and space-based missions, with their unobstructed, multi-wavelength capabilities, provides us with an unparalleled and ever-evolving picture of our dynamic Sun. These tools are the eyes and ears through which we decode the secrets of our star and predict its powerful influence on our cosmic neighborhood. Everything in the universe has a life cycle, and our seemingly eternal Sun is no exception. Stars are born, live out their lives, and eventually die, often in spectacular fashion. The Sun, like all stars, is undergoing a continuous process of evolution. While its current state of stable hydrogen burning has lasted for billions of years, and will continue for billions more, it is not immortal. Understanding its ultimate fate helps us comprehend not just the destiny of our own solar system, but also the lives and deaths of countless other stars across the cosmos. The Sun is currently in the most stable and longest phase of its life, known as the main sequence. It has been on the main sequence for approximately 4.6 billion years, and it will remain there for another 5 billion years or so. During this phase, it generates energy by fusing hydrogen into helium in its core, maintaining a delicate balance between the outward pressure of fusion and the inward pull of gravity. This is the period during which life has thrived on Earth. However, this stable phase won't last forever. The Sun's evolution is driven by the depletion of its core hydrogen fuel. Hydrogen fuel depletion. As hydrogen in the core is continuously converted into helium, the supply of hydrogen begins to dwindle. Helium, being denser and not undergoing fusion at the core's current temperature and pressure, accumulates in the core. When the core's hydrogen is largely exhausted, around 90% of it used up, fusion reactions will begin to slow down. Contraction and heating of the core. With less outward pressure from fusion, gravity will start to win, causing the helium-rich core to contract. This contraction increases the core's temperature and pressure dramatically. Hydrogen shell burning. The increased temperature and pressure in the core will heat the layer of hydrogen just outside the core. This will ignite a shell of hydrogen fusion around the inert helium core, a process known as hydrogen shell burning. This shell burning will be much more vigorous than the original core fusion. The expansion into a red giant. The intense energy generated by the hydrogen shell burning will cause the Sun's outer layers to expand dramatically and cool. As its surface temperature drops, its color will shift towards red. This is the red giant phase. The Sun will swell to an enormous size, far larger than its current diameter. Impact on inner planets Mercury, Venus, Earth. When the Sun enters its red giant phase, its radius is predicted to expand to eventually encompass the orbits of Mercury and Venus, consuming them entirely. The fate of Earth is a subject of ongoing research, but most models suggest it will likely be engulfed by the expanding Sun as well. Even if Earth avoids being physically swallowed, the extreme heat would boil away its oceans, strip its atmosphere, and melt its surface, rendering it completely uninhabitable long before it's engulfed. The surface of the Sun would effectively become Earth's new surface, vaporizing everything. This process is expected to begin in approximately 5 billion years. The red giant phase is a temporary, albeit dramatic, stage in the Sun's life. After about 1 billion years as a red giant, the Sun will undergo further transformations. Helium flash and helium core burning briefly. As the hydrogen shell burning continues, the inert helium core will continue to contract and heat up until it reaches a critical temperature, around 100 million degrees Celsius or 180 million degrees Fahrenheit. At this point, helium fusion will ignite suddenly and explosively in a runaway reaction known as the helium flash. After this brief flash, the core will stabilize, and the Sun will begin fusing helium into carbon and oxygen in its core. This phase is much shorter than the hydrogen-burning main sequence. Asymptotic giant branch, AGB phase. Once the helium in the core is exhausted, fusion will cease there, and the Sun will again start fusing hydrogen and helium in shells around an inert carbon-oxygen core. This leads to another phase of expansion, though less dramatic than the first red giant phase, known as the asymptotic giant branch, AGB. During this phase, the Sun will become increasingly unstable. The shedding of outer layers to form a planetary nebula. The instabilities during the AGB phase will cause the Sun to pulsate violently, shedding its outer layers into space. These expelled gases will form a beautiful expanding shell of ionized gas around the dying star's core, illuminated by the hot central remnant. This spectacular cosmic cloud is known as a planetary nebula. Despite their name, planetary nebulae have nothing to do with planets. They were so named by early astronomers because some appeared round and planet-like through their telescopes. These nebulae are often exquisitely beautiful, with intricate shapes sculpted by the star's remaining magnetic field and interactions with ejected material. The Ring Nebula and the Helix Nebula are famous examples. This process enriches the interstellar medium with heavier elements, carbon, oxygen, nitrogen, that were created within the star, making them available for the formation of new stars and planets in the future. A cosmic recycling program. The remnant, a white dwarf. After expelling its outer layers, all that will remain of the Sun is its incredibly dense, hot, and small core. This stellar remnant is called a white dwarf. Properties of a white dwarf. A white dwarf the size of our Sun's core will be roughly the size of Earth, yet it will still contain about half of the Sun's original mass. This means it will be incredibly dense. A teaspoon of white dwarf material would weigh several tons. It will no longer be generating energy through fusion, but will slowly cool down over billions and trillions of years, radiating away its residual heat, cooling an eventual fate as a black dwarf, over an unimaginable span of time, far longer than the current age of the universe. This white dwarf will gradually cool, dimming as it radiates away its stored thermal energy. Eventually, it will cease to emit significant light or heat, becoming a theoretical object known as a black dwarf, a cold, dark, and dense, stellar corpse. It's important to note that no black dwarfs are thought to exist yet, as the universe simply is old enough for any white dwarf to have cooled down completely to this state. The Sun's life cycle is a journey of stellar evolution, a cosmic ballet dictated by the laws of physics. It's a testament to the dynamic nature of stars, which not only provide energy for life, but also play a fundamental role in the cosmic cycle of matter, creating and dispersing the very elements that make up planets, and, ultimately, us. Our journey through the Sun's intricate layers, its dynamic activities, and its profound influence on Earth brings us to a crucial understanding. The Sun is not merely a distant light source, but a complex living entity that shapes our existence in countless ways. From ancient reverence to cutting-edge scientific inquiry, humanity's relationship with our star has continuously evolved, deepening our appreciation and sharpening our awareness of its power. We've delved into the Sun's majestic structure, revealing a powerhouse where nuclear fusion in the incredibly hot and dense core transforms hydrogen into helium, unleashing the energy that powers our solar system. We traced this energy's arduous journey outwards through the radiative zone, then its turbulent ascent, via convection currents, to the photosphere, the visible surface that greets us each day. Beyond, we explored the hotter, more enigmatic layers of the chromosphere and the million-degree corona, both driven by the Sun's powerful magnetic field. This magnetic field, a product of the Sun's solar dynamo, fueled by convection and differential rotation, is the orchestrator of all its spectacular activity. We've seen how it gives rise to sunspots, those cooler, dark blemishes that mark regions of intense magnetic flux, and how their cyclical appearance defines the 11-year solar cycle. More dramatically, we witnessed the explosive power of solar flares, sudden bursts of radiation, and the immense expulsion of plasma in coronal mass ejections, CMEs, events that send shockwaves through the solar system. Crucially, we examined the tangible impact of these solar phenomena on Earth, collectively known as space weather. From the mesmerizing beauty of the aurorae that dance in our polar skies, to potential threats to our modern technological infrastructure, including disruptions to radio communications, potential damage to power grids, and hazards for satellites and astronauts. The Sun's influence extends far beyond mere light and heat. Our planet's magnetosphere stands as a vital shield, protecting us from the brunt of the continuous solar wind and more extreme solar storms. Finally, we contemplated the Sun's vast cosmic timeline, understanding its current stable phase as a main sequence star, its inevitable future expansion into a red giant engulfing inner planets, its dramatic expulsion of outer layers to form a beautiful planetary nebula, and its eventual peaceful retirement as a cooling white dwarf, destined to slowly fade into a hypothetical black dwarf over eons. Despite our remarkable progress, the Sun continues to hold many secrets. The field of solar physics is vibrant and dynamic, with scientists worldwide working to unravel these remaining mysteries. Precise coronal heating mechanisms, while theories involving magnetic reconnection and waves are strong contenders. The exact mechanism, or combination of mechanisms, that heats the corona to millions of degrees, making it vastly hotter than the surface below, remains one of the most significant, unsolved problems in solar physics. Missions, like the Parker Solar Probe and Solar Orbiter, are specifically designed to gather the insight to data needed to crack this enigma. Solar cycle prediction. We understand the 11-year solar cycle, but accurately predicting the exact timing and strength of future solar maxima and minima remains challenging. Improved predictions are vital for space weather forecasting, allowing us to better prepare for solar storms. Deeper understanding of the solar dynamo's intricacies is key here. Magnetic field, generation, and evolution. While the Babcock-Lytton model provides a good framework, the detailed processes by which the Sun's global magnetic field is generated, sustained, and systematically reverses over its 22-year cycle are still being refined. Understanding these dynamics is crucial for predicting all solar activity. Origin of solar energetic particles, SEPs. While we know flares and CMEs accelerate particles, the precise mechanisms by which SEPs are accelerated to such incredibly high energies, and how they propagate through interplanetary space, are still active areas of research. This has direct implications for astronaut safety and spacecraft design, long-term solar variability, and climate connection. The nuanced relationship between subtle long-term variations in the Sun's output and Earth's climate remains a complex and hotly debated topic. Separating the Sun's natural influence from anthropogenic climate change requires sophisticated modeling and continued long-term solar monitoring. Future research will continue to push the boundaries, employing next-generation ground-based telescopes like DKIST, pushing the limits of resolution, and new space missions that will provide unprecedented vantage points and in situ measurements. The pursuit of these answers not only satisfies our curiosity, but also directly contributes to our ability to live and operate safely in space and on Earth. The Sun is more than just a source of light and heat. It is an active, dynamic star that plays an indispensable role in the grand cosmic narrative. Its life story is intertwined with the very existence of our planet and the flourishing of life upon it. The elements forged in its fiery core, and those dispersed by its stellar winds and ultimate demise, contribute to the vast cosmic recycling program that seeds future generations of stars, planets, and potentially, life. As we continue to explore the cosmos, our understanding of the Sun remains the cornerstone. It serves as our closest laboratory for studying stellar physics, a benchmark against which we measure the properties and behaviors of stars across the universe. Our evolving relationship with the Sun, from ancient awe to modern scientific mastery, underscores humanity's relentless quest to understand our place in the universe. It reminds us that we are not isolated, but intimately connected to the powerful, life-giving star that illuminates our corner of the galaxy. We've just embarked on an extraordinary journey into the heart of the Sun, from where its energy is forged to how it influences every aspect of life on Earth. The complexity and majesty of this star are truly astounding, and there's so much more for us to continue exploring. If you found this expedition insightful and valuable, please consider supporting Astronomical Library, so we can continue to bring you even more in-depth content on space science and astrophysics, like this video post, If you found this deep dive into the sun enlightening, a simple like will help us reach more curious minds like yours. Share with fellow enthusiasts. Do you know someone who loves space, science, or simply wonders about the universe? Share this content with them, and let's expand our community of cosmic explorers. Leave a comment below. Your thoughts and questions fuel our passion. What was the most surprising thing you learned about the sun today? Do you have any lingering questions? Let us know in the comments. We love hearing from you. Subscribe to Astronomical Library. Don't miss out on our next cosmic adventure. Hit the subscribe button and turn on notifications, so you're always up to date with the latest insights from the universe. Explore further. Questions for you. We believe science is a continuous dialogue. To keep the conversation going about the sun and the mysteries of the universe, let's ponder these questions. What do you consider the most significant discovery about the sun for humankind? Given our understanding of space weather, are you concerned about the sun's impact on our modern technology? How do you think we should prepare? If you had the chance to study the sun up close, like the Parker Solar Probe, what would you most want to investigate? In your opinion, is there a connection between the sun's variability and the long-term climate changes on Earth that we do not fully understand yet? Thank you for joining Astronomical Library on this cosmic journey. We look forward to seeing you in our next content piece.